Hello! Welcome to this tutorial on solid principles. This tutorial is for anyone who has some knowledge of any object-oriented programming language and want to develop or improve their skills of designing flexible and maintainable software. The examples in this tutorial use C#, but anyone with some experience on any object-oriented programming language can follow along easily. Let's first understand what is solid. Solid is basically a mnemonic acronym where each letter represents one principle. These principles were first introduced by Robert C. Martin, but the acronym was later introduced by Michael Feathers. So solid contains single responsibility principle, open-closed principle, Liskov substitution principle, interface segregation principle, and finally dependency inversion principle. We are going to look at each of these principles in detail with an example that violates this principle and then a refactored code which conforms to this principle. When designing software using object-oriented methodology, the solid principles help to keep the design readable, flexible, and maintainable. Now let's look at the first principle, which is single responsibility principle. The single responsibility principle is about how we separate or modularize code in object-oriented design. So this principle basically says that a class should have only one reason to change. If we naively apply this principle, we will end up with several classes where each class contains just one method and that just does one small thing. This leads to unnecessary complexity. This is clearly not what we want to achieve with this principle. Robert C. Martin, who first introduced this principle, clarifies that this principle is about people. Any changes to a class should originate from a single person or a group of people representing a department or business division or something similar within the company or organization that uses the application. If changes to a class is originating from more than one person or department or division, then the class is said to have multiple responsibilities and it violates single responsibility principle. For example, let's say we have a class called student that calculates grade for students and also tracks the books they borrowed from library. Any changes to this class can be requested by one of two departments. Teaching department may ask to change the way we calculate grading. Library department may also ask for changes to the way we record borrowed and returned books. So, two different departments are responsible for this class. In other words, this class fulfills different requirements of two different departments. If you are wondering why having a class that changes for more than one reason is not a good idea, then say a library department asks for some changes to the way books are borrowed. While making those changes for library department, there is a very high risk of breaking calculate grade method. This is because we don't know how the code is intertwined within the class. Even if you are careful and made sure the functionality of calculate grade method is unaffected, at the very least we need to ask teaching department to test the grade calculation, and this is not ideal. So, separating unrelated methods into different classes is a good idea, but at the same time, we need to make sure we don't end up with something called atomized class. When we say atomized class, we refer to a class that is unnecessarily designed to have very few methods which achieves very small thing. Robert C. Martin provided another complementing definition to clear some of the misinterpretation of this principle. He says, gather together the things that change for the same reasons and separate those things that change for different reasons. This complementing definition sort of says that we need to increase cohesion and decrease coupling of classes. This will help us to avoid atomized classes. With all these in mind, we can refactor student class. Let's create student grade class which just has calculate grade method. And then we'll create a new class called student library tracker, which has two methods, borrow book and return book. Now, student grade class only fulfills the requirements of teaching department, so it will only change for the requests from teaching department. Similarly, student library tracker class only fulfills the requirements of library department, and any changes needed will only originate from library department. If you see here, we have not split the original class into 3 different classes, each with one method. We have student library tracker class with 2 methods and student grade class with just one method. This is because we have taken the complementary principle into account and gathered borrow book and return book into one class because they change for same reason, and separated calculate grade to different class because it changes for different reason. I hope this helps you understand single responsibility principle. The next principle we are going to look at is open-closed principle. Open-closed principle says software must be open for extension but closed for modification. When we hear this the first time, it might sound like oxymoron, but it is not when we actually understand this principle correctly. This principle was first introduced by Burton Meyer, and he says software entities such as classes, modules, and functions should be open for extension but closed for modification. Later, Robert C. Martin provided an improved definition which is suitable for modern software development. He says you should be able to extend the behavior of a system without having to modify that system. Let's try to understand this in detail. How can a software be open for extension and closed for modification? After all, if we want to add a new functionality or change an existing functionality, we need to change the code. So, what this principle is actually talking about then? Basically, this principle says we need to identify changes that are frequent. Then we need to keep the parts of the system that are affected by those changes open for extension. And we need to keep the parts that are not affected by those changes closed for modification. Let's look at an example to make this clear. Let's say we have a class called accountant, and this class has a method called calculate tax. This method takes income as an input and returns the tax for the income. We can say this code conforms to open-closed principle as long as the calculate tax method doesn't need to be changed frequently. It doesn't need to be changed when the account class supports only one country and the tax rule or law for that country is not changing frequently. On the other hand, if we want to support tax calculation for other countries, then we can modify calculate tax method like this. Here we have different calculation per country. But the problem here is every time we add support for new country, the calculate tax method need to be updated. If we know that we are going to add support for more countries frequently, then accountant class is definitely not conforming to open-closed principle. To conform to open-closed principle, we need to make the code in calculate tax method open for extension, but keep the accountant class and its contract closed for modification. We need to keep accountant class and its contract closed because we don't want the consumers of accountant class affected whenever new country is added. If the contract of accountant class is changed, then we need to update all the existing consumers. On the other hand, if the calculate tax method itself is changed, then we have high risk of breaking existing functionality, so some or all of the existing customers may be affected. Neither of those are ideal scenarios. So, one of the ways of making accountant class conforming to open-closed principle is by using abstraction. We can create a tax calculation abstraction by using an interface. So we are creating an interface called iTaxCalculator, and this interface is going to have a method called calculate, and this calculate method is going to take income as an input and it is going to return the calculated tax. Now we need to change the constructor of accountant class to accept tax calculator instead of country enum as parameter. So this is the new version of accountant class that conforms to open-close principle. We can create concrete version of this interface for each country implementing tax calculation like this. Another example for open-close principle is plugin model implementation. Plugins allow extending the functionality of host program without changing its code. When conforming to open-close principle, more often than not, we might need to make some modifications, but those modifications are usually isolated and trivial. For example, when creating a new class supporting tax calculation for new country, the country enum need to be updated to include the new country, and any logic that we need to have to map country enum to the tax calculation class need to be updated as well. If we look at the essence of this example, it is all about swapping tax calculation logic at runtime. We don't necessarily need to use interface to achieve this. We can use higher order function, abstract class, or anything similar that allows us to swap code at runtime to get the same end result. Designing a software that conforms to open-close principle for every possible changes that may occur in the future is impossible. And trying to do that will only create unnecessary complexity and increase the cost of initial development. Robert C. Martin says, resisting premature abstraction is as important as abstraction itself. So, we need to identify what to design that conforms to open-close principle and what not to. Sometimes we can identify this by making an educated guess based on our experience or by talking to domain experts, but sometimes we need to wait until the first change occurs. Sometimes we may get it wrong and design something that rarely changes but conforms to open-close principle. So, as you guessed, the challenge is not in applying open-close principle but identifying what should be designed conforming to this principle. Next principle we are going to look at is Liskov substitution principle. Liskov substitution principle is about substitution of one object for another without affecting the program that uses those objects. Barbara Liskov introduced this principle and she says, what is wanted here is something like the following substitution property. If for each object O1 of type S, there is an object O2 of type T such that for all programs P defined in terms of T, the behavior of P is unchanged when O1 is substituted for O2, then S is a subtype of T. Let's understand this with an example. Suppose we have a class called music player which allows user to play music. We also have another class called trial music player which is inherited from music player class. The trial music player class overrides play method and allows only playing 5 songs in a day. We have another class called player widget. This class represents one of the user interfaces that user can use to control the music player, and it simply delegates user requests to the music player class. The essence of Liskov substitution principle is that we should be able to use objects of derived type in place of objects of base type without altering the behavior of the program that is using those objects. Only then we can call the derived type as subtype. In this example, trial music player is not qualified to be a subtype of music player because we cannot substitute the object of trial music player for the object of music player without changing or breaking player widget. This is because player widget is not built to handle the new exception thrown by trial music player when more than 5 songs are played. There are many subtle ways in which we can break substitutability of objects. There are some rules that we can follow to avoid breaking substitutability. The first one is no new exception. We should not introduce any new exception in the subtype. But it is okay to throw an instance of subtype of an exception which is thrown by the base class. The second rule is covariance of return type and contravariance of arguments in subtype methods. Let's first understand what covariance and contravariance mean. Covariance and contravariance come into picture
when we are dealing with complex type with one or more independent type components in them. Generics is one such type, so we use custom generic type called iSpecialist of T for our example. Let's say we have a base class called person. We have another class called employee, which is derived from person. In general, we can assign object of employee to type person, but assigning object of person to type employee is not allowed. This is not true by default for generic types like iSpecialist of T. We cannot assign object of iSpecialist of employee to type iSpecialist of person or vice versa. However, we can allow these assignments to work using variants. If we allow assigning the object of iSpecialist of employee to type iSpecialist of person, then we say iSpecialist of T is covariant. If we allow assigning object of iSpecialist of person to type iSpecialist of employee, then we say iSpecialist of T is contravariant. So in order to avoid breaking substitutability, the method arguments must be contravariant and return types must be covariant in subtype. In C#, you can create covariant interface using out keyword and contravariant interface using in keyword. The next rule is we should not strengthen the preconditions in the subtype. Preconditions are any validation that we perform before executing a method. Next rule is we should not weaken postcondition in a subtype. Postconditions are any validation that we perform after the method is executed. Another rule is preserving invariants. Invariant refer to properties or state that are preserved when the method is executed. Any such invariants of supertype must be preserved in subtype. The final rule is something called history constraint. As per this rule, subtype should not introduce a new method that allows mutating state that is immutable in supertype. The next principle we are going to look at is interface segregation principle. Interface segregation principle was introduced by Robert C. Martin, and he says clients should not be forced to depend on methods it does not use. There may be scenarios where we may have a class that has members such as fields, properties, or methods used by two or more clients. When changing any of the members used by one client, all the clients of the class, even the ones that are not using the changing members, are affected. Robert C. Martin describes these type of classes as interface pollution. In this context, interface refers to public members such as fields, properties, and methods of the class. As per interface segregation principle, we should have one interface per client with just enough members needed for that client. This is better understood with an example. Let's say we have a class called order. And this class has several methods like create, update, cancel, return, track, process, dispatch, process cancellation, process return. So if we look at these methods, actually, some of these methods are used by customer user interface, whereas the other methods are used by seller user interface. While it is best to avoid this type of classes, it is not always possible for various reasons. In situations like this, it is a good idea to have client-specific interface that exposes just enough members for each client. The key benefit of having client-specific interface are it allows clients to see only what it needs to see, so the collaboration between the class and the client is clear. Also, it completely eliminates the chance of misuse. For example, customer user interface calling dispatch method is completely eliminated. Martin Fowler calls this type of interface as role interface. So in our example, we'll create two interfaces, one for each client. The first interface is iCustomerOrder. So this has all the methods needed for customer, which is create, update, cancel, return, and track. And the second interface is iSellerOrder, which has all the methods needed for seller user interface. Those includes process, dispatch, process cancellation, process return. The order class still contains all the methods, but it now implements both iCustomerOrder and iSellerOrder interfaces. The customer user interface can use iCustomerOrder abstraction rather than order class directly. This way, customer user interface won't see any method that it should not see. Likewise, seller user interface can use iSellerOrder and it won't see any method that it should not see. The final principle we are going to look at is dependency inversion principle. Dependency inversion principle is introduced by Robert C. Martin, and his definition is twofold. First one is high-level modules should not depend on low-level modules. Both should depend on abstraction. And the second one is abstraction should not depend upon details. Detail should depend upon abstractions. Let's look at an example of hypothetical mortgage application system. We have higher level mortgage module with application class and bureau data module at the next level with bureau data provider class. And at lower level, we have a utility module with data cleaner class. Here, the higher level application class directly depends on next level bureau data provider class, and bureau data provider class directly depends on data cleaner class at the lower level. Application class indirectly depends on data cleaner. Now, changes to data cleaner or bureau data provider may directly affect application class. This is not a good situation. The higher level module should control the lower level module, not the other way around. Otherwise, changes in lower level module would force changes on the higher level classes and their consumers without adding any value. In addition to this, when higher level classes directly depends on lower level classes, it is very difficult to reuse higher level classes in different contexts. We can use dependency inversion principle to address this issue. We first need to define abstractions that higher level modules should work with, then make the lower level modules implement them. So we are creating an interface called iApplication Bureau Data Provider within the mortgage module and make the application class use the iApplication Bureau Data Provider rather than Bureau Data Provider class itself. And in the Bureau Data module, we have created a new interface called iData Cleaner, and Bureau Data Provider uses the iData Cleaner rather than Data Cleaner class. We have also changed Bureau Data Provider class to implement iApplication Bureau Data Provider interface. And in the utility module, we have changed the Data Cleaner class to implement iData Cleaner. Now let's fix all the references. Previously, mortgage module was referencing Bureau Data module, and Bureau Data module was referencing utility module. Now, mortgage module does not use Bureau Data, whereas Bureau Data module uses mortgage. Similarly, Bureau Data module does not use utility, whereas utility uses Bureau Data module. Now, the advantage of this design is that changes to Bureau Data Provider class cannot affect application class because Bureau Data Provider implements iApplication Bureau Data Provider and it cannot change the contract. Also, we can easily reuse application class with another Bureau Data Provider as long as the new Bureau Data Provider implements iApplication Bureau Data Provider. We need to understand here that it is not necessary that the interfaces higher level module depend on should be packaged in the same module. It can be in different module as long as it is owned by higher level modules. This principle is also referred to as Hollywood principle. This is because "don't call us, we will call you" phrase is used in Hollywood auditions, and this is the communication pattern we achieve with dependency inversion principle. That is it for now. Thank you for watching. See you in the next tutorial.